Hi class, this is a short video on using Kepler's third law to solve problems about objects orbiting the sun, which includes the planets. It also includes other objects like comets and asteroids. Anything that orbits the sun, we can use Kepler's laws of planetary motion to describe those objects, the orbits of those objects. Here is Kepler right here. He was a mathematician, and he worked with an astronomer named Tycho Brahe. And Tycho Brahe had produced the most precise measurements of the motion of planets at the time, and Johannes Kepler interpreted those and arrived at his three laws of planetary motion. The first of which is that planets travel along elliptical orbits around the sun, and the sun is at one focus of that ellipse. There's another focus, and there's nothing located there. So the planet follows this ellipse path right here, and it could be a circle. A circle is one type of ellipse. But actually none of the planets that orbit the sun take perfectly circular orbits. So they're all going to be what we would say is eccentric, which means kind of squished like this in one dimension. So when you look at this picture of an ellipse, we can see some of the major features of it, the important features. There's the major axis, which is the long dimension of the ellipse. There's the minor axis, which is the short dimension of the ellipse. And for us, in using Kepler's third law, the thing that we really want to pay attention to is the semi-major axis, which is nothing more than half of the major axis. So if you know the major axis, you just divide that by 2 and you get the semi-major axis. And that's the thing that we're really going to want to pay attention to. And while we have this slide open, I'll point out two other things. There's this location right here, the aphelion. This is the position of the planet when it reaches its greatest distance from the sun. And right here is the perihelion position. And this is where the planet is located when it reaches its closest proximity to the sun. And sometimes when you see problems involving Kepler's third law, what will be specified is the distance from the sun to the aphelion, which is sometimes called the aphelion distance, and similarly for the perihelion, the problem would provide the distance from the sun to the perihelion. Well, look at what you can do with that information. If you know these two distances, the aphelion and the perihelion, you can add them together and you get the major axis, and then you can divide that in half and you get the semi-major axis. So the semi-major axis equals this distance to the aphelion plus this distance to the perihelion divided by 2. You divide that sum by 2. All right, so very quickly, this is Kepler's first law. Kepler's second law is the one that says that planets sweep out equal areas in equal times. And the important result of that is that planets, they speed up when they're closer to the sun and they slow down when they're further from the sun. But this video is about Kepler's third law, so let's get to that one, and this is it. Kepler's third law, p squared equals a cubed. What does that mean? P is the orbital period of a planet or a comet or anything orbiting the sun, and it's measured in years. So the orbital period squared, so if you take the period in years squared, that's going to equal the semi-major axis A cubed. And remember, the semi-major axis is this distance right here, half of the major axis, and the semi-major axis must be expressed in astronomical units. You'll remember that an astronomical unit, by definition, is the average distance between the Earth and the Sun. Now we have another way of saying that. An astronomical unit is the semi-major axis of the Earth's orbit around the Sun. And so for the Earth, the period is 1, The semi-major axis is 1, and look at this, 1 squared equals 1 cubed. So that's the very trivial example of using Kepler's third law. Now we'll do a more interesting problem. And this is the type of problem that you'll see on your homework and you expect to see on a test. The planet Jupiter orbits the Sun along an elliptical orbit which has a semi-major axis of 5.2 AU. How long does it take for Jupiter to complete one orbit around the Sun? So Jupiter has a semi-major axis of 5.2 AU, which means that on average Jupiter is 5.2 times more distant from the Sun than Earth is. So here we go. We're given the semi-major axis and it's already in astronomical units, so it's all ready to plug into Kepler's third law, which is right here, which tells us that p squared equals a cubed. We're given a equals 5.2, so we plug that into Kepler's third law and we compute this. So you use your calculator for this. 5.2 cubed is 5.2 times 5.2 times 5.2, and your calculator will tell you that is 140.6. And this number right here is the orbital period squared. So we're not done yet. We want the orbital period. And the step that we do to solve for the period is we take the square root of both sides of this equation and we get this. The orbital period equals the square root of this number, 140.6. Use your calculator to do that and you get 11.9, and this is the orbital period measured in years. So it takes 11.9 years for Jupiter to complete one orbit around the Sun, and that's because of its semi-major axis being 5.2. So that's kind of interesting. This is a different type of problem using Kepler's third law. So as I stated at the beginning of this video, we can apply Kepler's third law for any object, including something kind of crazy like this, Halley's Comet. Look at this picture down here. There's the Earth's orbit, Mars, Jupiter, Saturn, Uranus, Neptune. This comet, it goes way out near the orbit of Pluto, and then it comes into the inner solar system and it passes by Earth. And that last happened around 1986, and this, you would see this every night in the sky. Ask your parents about it if you weren't alive back then, which I'm assuming you weren't. So here we go. Halley's Comet orbits the Sun along a highly eccentric ellipse. So that's it, you know, going, it's really flattened like that. The aphelion of this ellipse is 35.1 AU from the Sun, and the perihelion of this ellipse is 0.6 AU from the Sun. It gets very close to the Sun. Calculate how long it takes for Halley's Comet to complete one full orbit. And so what we can do is we can go back to this picture, and if we're given this distance and if we're given this distance, we can add those two together to get the major axis, and then we can divide that in half to get the semi-major axis. So that's what I've done right here. The semi-major axis is 35.1 plus 0.6, and we divide that by 2, 17.85. And so at this point, now that we have the semi-major axis, now the problem becomes identical to the previous one. So we just plug this into Kepler's third law. So we now know that A is 17.85 AU. So we plug that into Kepler's third law. 17.85 cubed, your calculator will tell you that's 5,687. And then finally, to solve for the period, we would take the square root of both sides, and the period is 75.4 years. So that's how long it takes for Halley's Comet to make one full orbit, and it was last in the inner solar system, wherein we saw it in the night sky in 1986. And using this orbital period, we can now predict that 75.4 years after that it's going to return, and that will be in 2061. So that is what you can do with Kepler's third law.